So I'm glad to be here today. I'm going to talk to you about some work that I've been doing to develop ways to link our sediment transport calculations to geochemical processes. So I'm going to show two examples. And both of these examples have in common that what we've done in terms of model development is we've added reactive tracers to our sediment transport model. In the first example, we're using this ability in order to link our sediment transport to biogeochemical models by including diagenesis within our sediment transport calculations. And then after I present that, I'm going to show you an example where we're using our reactive sediment tracers to account for radioisotopic profiles, again, within our sediment transport model. So in the first example, the motivation for this was that we're developing good models of sediment transport, but they have limited ability to tell us much about what's going on with biogeochemical cycles. Meanwhile, our colleagues who are biogeochemists have been developing their models, but they often have to rely on simplifications about what's happening on the sediment bed itself. So in order to try to close that gap, the approach I've taken is to try to account for the biogeochemistry within my sediment transport model. A lot of the work that I'm going to present has been part of the Mechanisms Controlling Hypoxia program, and within that program, which has been mostly funded by NOAA, we've developed a suite of numerical models within the Regional Ocean Modeling System. So ROMS is a 3D hydrodynamic model. Within MCH, we've developed three models within ROMS. Kind of the framework of our models is the physical oceanographic model developed by Rob Hetland. So this is a plot of Rob Hetland's showing his model grid and the salinity fields that he estimates within his model of the northern Gulf of Mexico. So this is the Mississippi Birdfoot Delta, and this is freshwater coming from Atchafalaya Bay. Now, since we're funded to explore the processes that impact hypoxia, we've used Rob Hetland's framework of his physical oceanographic model, and we've built two different models within that framework. So the one that I've worked most on was a coupled sediment transport physical oceanographic model that I worked on with Kevin Hsu, who at the time was a postdoc with me at VIMS, and now Kevin is at LSU as a faculty member. So Kevin and I linked our sediment transport model to the ROMS hydrodynamic model, and in doing that, we estimated suspended sediment fluxes, net erosion and deposition for the northern Gulf of Mexico, and we published a paper in 2011 where we analyzed model fields for calendar year 1993. In order to develop our sediment transport model, we took Hetland's hydrodynamic model, and here's a plot of the hydrodynamic model grid showing two sources of fresh water to the northern Gulf of Mexico. And then to account for sediment transport within the hydrodynamic model, we need to add something to the vertical grid. So this here is trying to show a model grid cell in the horizontal, and then we zoom in to see what it looks like in the vertical, because this is a fully 3D model. So what we do to account for sediment transport is we add a sediment bed model underneath of the water column model. So here the blue cells represent the water column, and within the water column we're calculating the fluxes of salinity, temperature, momentum, and suspended sediment concentrations. Underneath our hydrodynamic model, we have a model of the sediment bed. So when we have flux convergences or divergences of sediment, that gives us net deposition and erosion to our sediment bed. Our sediment bed model is made up of a series of bed layers that are each about 1 millimeter thick, and within each of those sediment bed layers, we keep track of the sediment grain size distribution and the erodibility of the sediment. And then we use a basic transport equation. This is a transport equation we use for sediment in the water column. So I just put this up here to note that our time-dependent sediment concentration fields are subject to advection and diffusion in source and sink terms, but there's no reaction terms. This is an advection diffusion equation, not an advection diffusion reaction equation. In our 2011 paper, Kevin tried to relate our sediment transport estimates and our physical processes in the model to hypoxia. So this is a plot of the observation of hypoxia observed by Nancy Rabelais in the summer of '93, and then Kevin overlays that with physical forces or physical processes that he got from the model. So this is stratification, this is suspended sediment concentration, and this is a maximum erosional depth. So in the paper, we argue that perhaps there are hints that the physical processes that are going on are important for hypoxia. So hypoxia is defined as the occurrence of low oxygen levels that tend to occur every summer in the northern Gulf of Mexico and tend to be constrained to the layers just a few meters above the bed. But in trying to make these kind of links between the sediment processes and hypoxia, we really had to do, admittedly, a bit of arm waving because our sediment model doesn't account for oxygen dynamics. Concurrently with our developing the sediment model, our colleague who is a biogeochemist, Katja Fennel, has been coupling her model of biogeochemistry to the same hydrodynamic model that Hetland developed. This is a schematic of the processes that are included in the biogeochemical model. It's an NPZD model, so it resolves the nitrogen cycle. And what's important for us is that when we have blooms of phytoplankton and zooplankton, those create detrital particles. So in Fennel's model, she would call these small and large detritus. And what her model has done historically, the way she's run her model, is when these detrital particles sink to the bed, they're instantly remineralized. So they carry organic nitrogen to the bed, and then immediately that releases, through denitrification and aerobic remineralization, that releases ammonium and nitrates and serves as a sink of nitrogen to the system. So in her standard model, there's no accounting for lag times in remineralization of the organic matter. There's no accounting for burial of organic matter, and there's no accounting for redistribution of these particulate organic matter through things like resuspension and deposition. In this paper was just published last month, and in this paper, she compares her estimates of hypoxia to the observations. So these black dots represent Nancy Rabelais' observations of hypoxic bottom boundary layer water during the same time frame that Katja Fennel ran the model. The red indicates locations in the model that were estimated to be hypoxic. And a big point of this paper is that the way that the model accounts for sediment oxygen consumption, that the hypoxia predictions were very sensitive to the way that the model accounted for sediment oxygen consumption. So in her standard model, where she assumes that sediment oxygen consumption only follows this instant remineralization, she gets reasonable estimates of the areal covered by hypoxia, but her hypoxia is too shallow. When she does another assumption where oxygen consumption only depends on temperature, so it's going to be timed with the summer instead of timed with the productivity blooms, she gets, again, reasonable estimates for the area covered by hypoxia, but she gets a hypoxia in areas that are deeper than it's commonly occurred. So we've wondered if we could better account for sediment oxygen concentration, would we come up with a tool that we could better use to understand the mechanisms that control the spatial extent of hypoxia and the temporal processes that initiate it. So in order to do that, I've been charged with trying to work on the missing link. So the missing link in our suite of models was a connection between the sediment transport model and the biogeochemical model. And so what we have gone forward with doing is to try to develop a model of diagenesis that will allow for burial of that organic matter and time lags in the remineralization of the organic matter. The diagenetic model that we chose to implement was this model by Sodert. We chose it for a few reasons, one being that it's a nitrogen-based model, as is Fennel's model. And then another reason is that, like our sediment transport model, it resolves its tracers in layered sediment bed. So it resolves millimeter scale sediment beds, but it's keeping track of the concentrations of pore water, oxygen, pore water, nitrate and ammonium, and particulate organic matter with depth in the bed. So its model grid is really similar to the model grid that we're already using for sediment transport. One distinguishing factor about Sodert's model is she does not try to explicitly account for things like the iron and the manganese and the sulfate cycles. Instead, she lumps all of that into what she calls oxygen demand units that build up in the anoxic sediments. But like most diagenetic models, Sodert's model assumes that we have slow, steady accumulation of sediment. So they're typically were developed for deep sea environments where you could assume slow raining of particulate organic matter so that our pore water species and organic matter is slowly advected downward in our sediment core. But we wouldn't necessarily think that this slow, steady sediment accumulation is valid for energetic coastal environments, where instead we're going to have rapid episodes where we can erode and redeposit millimeter to centimeter scale layers of the sediment bed over the periods of hours to days. So in order to try to account for those resuspension processes in diagenesis, I've done something that is a little crazy, which is put the diagenetic model within the sediment transport model. So here's what we did. Here's again our model grid. We've got the water column. So now our water column accounts for sediment, the sediment classes, salinity, temperature, as well as all of Fennell's biogeochemical tracers. But now on our sediment bed, we've modified it so that not only do we account for sediment grain size, but we also keep track of particulate organic matter, dissolved pore water species, and in each of our bed layers. We also added biodiffusion to the model, which was not in there before, so that we can have diffusion across our sediment layers. Now, our stuff on our sediment bed is exchanged with stuff in the water column through two ways. One is diffusion of pore water through the sediment water interface, and then the other is when we have cycles of resuspension, we take any material that's eroded, we put that up in the water column, and then when we redeposit material, we add whatever particulate organic matter to that would be deposited to the layer of the bed, and then we create new pore space that has the same concentrations of the dissolved species as the overlying water. So this is, I call this the scary wire diagram. This is truth in advertising. This is what is in this model. And the first time I drew it up, I was really, I'm still scared of it, honestly. But when you back up and you think, okay, this is what we started with. We started with Fennell's model, which is very well accepted in the biogeochemical community. We started with John Warner's community sediment transport model, again, which is, this paper that he wrote has 300 citations and came out in 2008. It's very widely used. So I started with two robust, accepted models from their respective communities, and I added links between them. So what I added are these kind of, I tried to color them kind of sage green, and so I added organic matter that sticks to my sediment, goes down to the bed. Its source is the detrital classes from Fennell's model. Once it's in the bed, it undergoes diagenesis and impacts pore water tracer concentrations, and then the pore water tracer concentrations are exchanged with Fennell's tracers through diffusion across the sediment water interface and cycles of erosion and deposition. I'm going to show you three different model runs. The first is kind of not very interesting because it's kind of like a standard diagenetic model where we assume steady processes. We assumed kind of no resuspension. So we start out with our initial conditions, and after 10 days of running the model, our sediment bed profiles don't look too different. So each of these panels is like we had a sediment core and we plotted the first 5 centimeters of the sediment core. The black line's the sediment water interface. The dashed line represents the zone of an energetic bioturbation. This is the organic matter in the bed. This is the remineralization rate of that organic matter. This is the oxygen concentration profile, the nitrogen species, and the oxygen demand units. Next, I'm going to show you how the system looks when we incorporate erosion and deposition. So I took a 20-meter site on the Louisiana shelf, and we got the wave time series from WaveWatch 3. So here's the wave heights. This is the bed stresses calculated by the ROMS model. So whenever bed stress exceeds about 0.1 Pascal, we would have resuspension. The bottom panel shows the model estimates for erosion in blue and suspended sediment concentrations in red. So our peak wave event, which was about a 3-meter wave that occurred on day 170 of the model, eroded about 2 millimeters of sediment. And then here, this shows what's going on in the organic matter that's in the water column. So we see whenever we have resuspension events, we stick some particulate organic matter up in the water column. So this is how the system behaves in time for this particular model run. So here the black represents a sediment-water interface, and so whenever it goes down, that was an erosion event. Whenever it goes down, we pulse oxygen into our sediment bed because the overlying water is oxygen-rich. We also pump organic matter into the bed when we go through a resuspension cycle. And when we go through an erosion cycle, we bring these anoxic sediments that have things that really want to suck a lot of oxygen up toward the sediment-water interface. So we enhance our oxygen consumption 3 ways. We bring the anoxic sediment up closer to the sediment bed during erosion. Then during deposition, we plump a lot of oxygen down on the bed that can be rapidly consumed by those reduced, by the ammonium and the oxygen demand units. And we also, in this model, add organic matter to the bed during a deposition cycle. When we look at how it behaves in time, this is the oxygen inventory on the bed. So whenever I have a resuspension event, in this model, I pump a lot of oxygen onto the bed. This is the oxygen consumption rates. And so the total consumption, again, has big increases when we have resuspension events. And I was interested to see that in this model run, most of the oxygen consumption is coming from exposure to the anoxic sediments. Now, I actually didn't so much trust that I thought I was pumping too much oxygen into the bed. So I looked into how the model was behaving, and I actually think this is a better representation of the shelf. I made the surface sediment layer thinner so that when I had erosion and redeposition events, I didn't pump as much oxygen into the bed. But the system behaves the same, just kind of with less of a signal for pumping oxygen into the bed. So next, I want to look at how oxygen consumption compares for 4 different model runs. So the solid lines compared to the dashed lines are model runs that included resuspension and model runs that did not. So we see that we get about the same baseline oxygen consumption when we include resuspension or not, but when we time integrate the oxygen consumption to get a cumulative sediment oxygen consumption, we get in this model run about 10% more oxygen consumption when we include resuspension than when we don't. And then I was still concerned that I was pumping too much oxygen into my bed, so I did a sensitivity where I compared the diffusion rate of oxygen across the sediment-water interface. Here I had a high diffusion across the sediment-water interface, here I had low, and it interested me that I got such spiky behavior in the oxygen consumption when oxygen is kind of limiting and I have low oxygen supply to the bed, but the overall cumulative effect was that oxygen, if I don't let a lot of oxygen diffuse onto the bed, I get about 50% less sediment oxygen consumption. So to summarize what I'm doing with sediment biogeochemistry is we've coupled these models, and I don't really know of another group that's coupled sediment transport like this to diagenesis, but we've done it, and I actually think, to some caveats over some timescales, I'm actually happy with how it's running. The results indicate that cycles of erosion and deposition can increase sediment oxygen bed consumption on the bed, but it's been really sensitive to this diffusion of oxygen and other pore water species across the sediment-water interface. So what I want to do with this next is, in the model run I showed you, my water column is well mixed. I don't have a hypoxic bottom boundary layer. So next I want to kind of nest my calculations within Fennell's 3D model so that I can look at when that anoxic sediment is resuspended, does that act to draw down sediment in the very near bed bottom few meters where hypoxia is occurring. And I want to try and apply it across spatial scales so that I can see if areas that tend to be depositional might be more likely to experience hypoxic conditions than other areas. Now I want to change gears and think about our second problem, that we've had difficulty for a long time synthesizing our model estimates to field data that relies on geochronological tracers. But we can address this problem the same way by adding reactive tracers to our sediment bed. This is a model run by my student Julia Moriarty. She did this for her master's as part of the NSF Margins program. Julia has been developing a 3D hydrodynamic model within ROMS of sediment resuspension offshore of the New Zealand Waipoua Shelf. So there's a river that puts sediment and fresh water into this embayment, and in this model run, she's in this animation, the blue line here is river discharge, the teal colored line is wave height. So she's showing a resuspension event during a flood. So what we're getting out of the model is deposit thickness and sediment fluxes. And then we've been trying for 10 or 20 years to compare our estimates of sediment deposit thickness to what we get from field sediment cores. So here's Julia Moriarty's sediment thicknesses. This is Tara Niskern, who's a VIMS researcher. Tara went out 10 days after a flood and collected cores on the sediment bed to see where she thought flood sediment had been deposited. The way she identified flood sediment was for looking for this terrestrial tracer beryllium-7. So these, wherever the dots are bigger and more colored brown, that is where she saw sediment that, because it was tagged with beryllium-7, she could infer that it had been on land within the past few months, because beryllium-7 has a half-life of 53 days. So for a long time, we've tried to compare these beryllium-7 estimates to the model estimates, and it's kind of comparing apples and oranges, because a lot of different things can affect beryllium-7, like bioturbation and dilution by seabed sediments. So what we can do is we can take that big scary wire diagram and pare it down and only account now in our reactive tracer bed, I only need to account for how these radioisotope tracers behave that stick to my sediment. So we're accounting for 2, beryllium-7, which is a terrestrial sediment marker, and we're accounting also in this model run for thorium, which is a short-lived radioisotope that tells me that the sediment had been resuspended in ocean water within the past few months. So where we're going with this is, again, using a model and now we don't just predict grain size distributions and deposit thicknesses, but we also estimate the radioisotopic profiles. And we can use that to evaluate the sensitivity of the radioisotopic profiles to things like resuspension that would dilute it, and also biodiffusion that would mix it in the bed. So this was a panel that my student Justin Birchler did at Ocean Sciences last year, and he's comparing the numbers that we typically get from field data is maximum depth of beryllium-7 penetration and the surface activity of beryllium-7, but here he's showing that for the same flood event that these numbers can vary depending on how intense resuspension is and how intense bioturbation is. So to summarize what we're doing with the radioisotope models, we're developing this linked geochronological sediment transport model, and the motivation is that I think it will help us with interpreting field data and comparing our model to the data. And then I'm just going to close with, I wanted to present this stuff in this meeting, CSDMS 2.0 moving forward. It's examples of using a community model for trying to address interdisciplinary problems, which is really challenging, but I think that working within a community model framework, that gives us really useful tools for the reasons that I've outlined here. Thank you.
So I'm sure Courtney will take some questions.
This is really interesting talk. I really enjoyed it. The one question I have when you talk about, I remember earlier you mentioned in the summer you have hypoxia, right? So are there temperature effect on the hypoxia process? Is that right? Or oxygen consumption?
Well, it's why is there hypoxia in the summer?
Yeah, you talk about that in the earlier, but not later in the results part. What is it?
Well, in the 1D model, I don't quite understand the question. In the 1D model, the 1D model that I showed, where I showed the diagenesis, I'm not modeling hypoxia in the water column. So I didn't account for seasonal effects in that 1D model.
No, I'm talking about the later part you showed. Yeah, these ones. These one you showed low supply, high supply of oxygen, and how they affect.
That's not. That is. I varied the diffusion rate across the sediment water interface. So the water column was still still had normal levels of oxygen. But to diffuse sediment from the water column into the sediment bed, I used a diffusion coefficient, and I varied that in order to but I varied it because I thought it was too high. The way the Sodert model, actually this is what I spent a lot of time on last week trying to get ready for the talk, was the Sodert model assumes, I'm trying to go back to the Sodert model, it assumes that the sediment surface is completely equilibrated with the overlying water. So in her model, she sets the pore water concentrations in that upper millimeter of sediment equal to the overlying water. So it's like you've had complete diffusion across the sediment-water interface. And that might be fine for a deep ocean environment where you have very slow processes going on, but I think in an energetic coastal environment, we wouldn't want to assume that. So for that sensitivity test I showed right at the end, I made that diffusion much slower so that I wouldn't immediately reset the concentrations equal to the overlying water.
Mm-hmm. Okay, thank you.
What do you think the physics is that's controlling the diffusion across the sediment-water interface? Is it the fluctuations of the pressure from the waves? Is it the turbulent boundary layer?
Well, I've tried to read up on it. It's not, but I think that the literature argues a lot for the boundary, that the oxygen profile has a boundary layer just like our suspended sediment concentration profiles have. And so you need, there are very complicated models that account for diffusion across the sediment-water interface and scale it with the bottom shear stress. In this model, since it's already so complicated, I've tried to use much simpler, just use a constant diffusion coefficient. But since my bottom water grid cell is like a meter thick, you know, the ROMS model doesn't resolve that boundary layer dynamics. So I could see that it might be interesting to try to account for some of the more realistic behavior of the oxygen profile close to the bed once in later studies.
It's a very interesting work, but just to make this even more complicated, what do you think maybe in the future, how will you consider, for example, the effect of consolidation in the bed?
Yeah, that's really where my approach is gonna run into problems. We have a model of ROMS that can account for consolidation, but in my model, I take the diagenetic model, which is an advection diffusion model, and I take the advection part out because I just add layers back on the bed. But if you were worried, when you want to account for longer timescales, when you need to account for compaction, then as the sediment bed compacts, that gives you an advective term in the pore water species where they advect upward. And I think that's something that it will be something that we'll have to tackle, I feel like, later. And I wouldn't want to apply the model over the timescales by which compaction would be important.
Really, really excellent talk. I thoroughly enjoyed it, especially the end was all the integration. I'm just asking this out of left field because I really don't know much about this, but is the type of clay that gets deposited during floods different than the types of clays that may get distributed on the bed, not during floods? Are the clays, because I know that lots of things adhere to them, does that make a difference?
I think in some systems, the material that comes out in a flood is going to be really different than what's on the ambient floor ahead of time. In other systems, what's on the seabed is the product of the floods that might have came last year, and so the mineralogy might not be that different. So I think it depends on the system.
I was just thinking particularly for the Mississippi. That was all.
For which, I'm sorry?
The Mississippi Gulf.
For the Mississippi, I don't know, really. I've looked a lot at the grain size distributions, but not the mineralogy. So.
Right. Maybe something interesting.
Probably people in this room who know more than me about that.
Okay, we'll go to Chris.
Thank you. This is my computer, so they need to swap.
Okay.
Sorry, we should have done that.
Everybody happy? Oh,